Okay, so let's get started. Hello,
Yes,
everyone.
sure.
Uh, Good evening, everyone. So, welcome to you all. Myself, Subhash from BS in Electronic Systems program and a member of CDC 2.0 organizing team, Circuit Design Competition as part of the Paradox 2026. I would like to welcome you all to this industry talk organized as part of CDC 2.0. At CDC, apart from the competition itself, we also wanted to create opportunities for students to interact with people from academia and industry and to get a glimpse of what technologies that power the devices we use every day. Today we have with us Mr. Arpan Thakkar, an analog design engineer at Texas Instruments India. Mr. Arpan completed his BE from Dharmesh Desai University and his MS from IIT Madras. Before joining Texas Instruments, he worked as an embedded hardware design engineer at Matrix Cosmic. Since 2017, he have been working with Texas Instruments at RF on RF clock generation and distribution systems, frequency multipliers, and voltage controlled oscillators (VCOs). He also holds four granted patents and has also authored nine IEEE publications. Today's talk is titled Clocks, Basics and Applications. Whether it is a smartphone, laptop, communication systems, or a processor, clocks play a crucial role in keeping everything synchronized. I'm very sure today's session will help us understand this important concept and its real world applications. Without further delay, I would like to pass the mic to you, sir.
Okay. Thanks for the kind introduction. Am I audible, right?
Yes, sir, you're audible.
Okay, okay. So I will go ahead and share my screen. So basically, I am a student of, I passed out in 2017 and I did the MS under my professor Anithan, and that's how I got to know about the stock. And I would like to share a few insights. So basically, in this talk, I have kept it like very general so that students from even first years can understand it. So don't feel like it's a talk and you have to listen to it in Q&A and wait till the end. Don't think like that. Any moment, if you feel that I'm going too fast or if you have any specific questions, please feel free to interrupt me and uh, ask your questions. Okay. So as Subhash said, let's get started, and I'll share my screen. Please let me know if you can see it. Just one second. Yes, there is one tiny hiccup. I'm not able to. Just one second. Can you all see my PPT?
Yes, sir, it's visible.
Okay. 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 So, title of the talk is clocks. You may be already aware of it. If not, then also it's fine. It plays a very crucial role in analog design, which is very crucial part of VLSI systems, RF systems, and all. So basically, there are three three basic circuits are there. One are clocks. One is amplifiers, which are linear circuits, and the third part is ADCs. Right. So basically, if you see the entire analog world, right, it revolves around these three basic things. So today I would take you through the very basics of clocks and how it enables different applications. Okay. Okay. So let's start with the very basic question that why does each mobile pick at exactly same time, right? So if you see your mobile or laptops or anywhere, anything you see, right, all show the same time. So let's try to understand how does it happen. Okay. So if you see this picture, yeah, if you see this picture, right? So this is like very dense picture, but if you see, it's nothing but first. first part of it is GPS discipline clock, right? So basically satellites have a very excellent purity clock, and why it is so, that also we will see. But after that, after GPS satellite, because it's every time your laptop or mobile will not have a GPS access, right? So if GPS has very synchronized clock, all your devices will be synchronized if you get to connect to GPS. But every time it's not possible, right? So how does it work is, you first there is a GPS. After that, there is something called local master clock. So this master clock is also having a very good purity, but not as good as the GPS satellites, but still they are very good. And after the local master clock, it reaches to your devices, um, all your lab PCs, or all your mobile, or any other timing device, right? Whatever you see. So either it is transmitted through the Ethernet or coaxial cable or wireless data. So that's how the distribution happens. And we note here is clock is not just one source that is in GPS. So in the absence of GPS also, let's say this, for some reason, local master clock, right? Whatever is displayed here, right? That also loses GPS signal, but it will still keep working because it will have its own clock. Only thing is that whenever the master clock is available, it will synchronize its own clock to master's clock, so that you get a very accurate clock. And same things happens to all your laptops or mobiles or everything. Okay, so so whatever I said, right? That let's say there are some clocks, crystal local clock is present. So in that local clock is made of quartz crystal oscillator. Okay, and that through some circuit, whatever frequency accuracy we get through the quartz crystal oscillator, right, that will be corrected through the GPS clocking. Okay, so now let's answer our first question, that why does GPS has very accurate clock? Because it doesn't depend on any material or something like quartz crystal oscillator. We'll discuss what is this quartz crystal oscillator is there. We'll discuss that. But it doesn't depend on any material or something. It is because it is derived from an atomic clock. So atomic clock is pure atoms vibration. Okay, so let's say cesium-133 atom that vibrates like almost 9 billion times per second, and this vibration doesn't change because it's a atomic vibration, right? It never changes irrespective of temperature or vibration. Whatever you put through it is always going to vibrate at the same times per second. Okay, so if we take that one as a reference and build oscillator around it, right, so that clock is going to be very, very accurate. Now, once you have one accurate clock, what you can do is, even if you have a quartz oscillator, you can always go and correct quartz crystal oscillator frequency with the atomic clock. Okay, so just to give you just feel that what if GPS suddenly disappears, right? So whatever this master clock is there, that takes around 30,000 years to lose 1 second. So sometimes we see, right, our wall clock and all, they get delayed, right? So once they get delayed, that we will get to know that, okay, it is running 2 minutes late or 5 minutes early or something like that. So from that sense, if you want to see, so this is so accurate that it takes 30,000 years to lose a 1 second, right? This master local clock, and this GPS clock is even more purer than that. Okay, so it basically it never changes. Okay, now if you compare that with your PC or lab servers, right, it is like every day you lose 1 second. So what does that mean? If you don't connect your PC to your GPS or internet, right? GPS you can't connect most of the time. We connect our mobiles to it. But if your laptop, right, it gets synced through the Ethernet, because finally that accuracy is propagating through the Ethernet, because GPS will go to master clock. Master clock will give signals to the Ethernet, and Ethernet will send those packets to your laptop and PC, and that's how it gets synchronized. Okay, so if you don't have access to the internet, you lose almost 1 second in one day. So that is what it is. Now you might feel that this is a very good accuracy, right? Why do we even need GPS satellite and all that? But now if you think about the entire banking system, right? So once the transactions are happening, at what time, so across the entire world, it has to follow a standard time, that this time this transaction happened. It should reflect in entire banking system wherever you see in the entire world, right? If we forget about the time zones, okay. So without that, what will happen is there will be a lot of problems, such as like this transaction got credited then at this time, but it shows in other systems it credited 5 minutes before or after, right? So those all things can cause big problems. So we need really good accurate clocks, and that is why we get synchronized to this GPS, which use ultimately the atomic clock. Now, if you compare it to the digital wall clock that initially I was talking about in the older days, right? So they are very cheap cords we use inside it. So there we lose 0.5 to 2 seconds in every 12 hours or 2 days. Okay. Now, if we really need good clock, why don't we use this atomic clock everywhere? The reason is simple. Whatever is very pure or something, right? It's usually very costly, and not just in terms of the money, but also in terms of the hardware, right? So it it can be really bulky, and let's say it has to maintain some minus, maybe almost Kelvin, minus 273 kind of a temperature, right? So in those cases, those kind of things, it's not possible to put it in all commercial devices. So that's the reason we have this kind of hierarchical structure where GPS has the best clock, and then it gets synchronized, and that same accuracy gets on passed to the all other our devices. So now let's talk about what is this quartz crystal oscillator. Any doubts till this point?
Sir, I have a doubt actually.
Okay.
So, as discussed, like it's a very basic doubt. So, in my junior, I just studied this that sees like how we calculate 1 second. So, as mentioned on the slide that if a cesium 130 atom vibrates 6 times per second, then that is 1 second. It vibrates one.
Sorry, I am your voice became very small.
Oh, is it 1 second?
Yeah.
I'm
Go ahead. Repeat, please.
Am I audible now?
Yes, you are audible.
So I was just saying that, as mentioned on the slide, that a cesium 133 atom, if it vibrates x time, then we count it as 1 second. So how actually we count that number and say that okay, it counted x times, now it is 1 second.
So actually, you don't count it and say like that is a 1 second. So what we do is it okay. So it vibrates certain amount of time. So that is nothing but it is producing a frequency of that high number. Okay. So once you have that high number frequency, what you do is you try to just keep anything if you want to measure or something, right? So you actually don't have to necessarily measure it. What you have to, once we have this count that let's say in 1 second it can because that you can anyway do, right? Let's say how you measure your distance, like in let's say two people are running, and then you start a timer, and then you see that how much time in certain time how much distance they have covered, right? So similarly in every 1 second, what we count is how much time that sine wave frequency is repeating. And at that frequency, if it is not possible to do it, what we do is we put frequency dividers. So I will cover those frequency dividers also in this talk. So what we do is we try to divide down those frequencies by that many time, and then we count that this is our total 1 second time. In that, how many times we saw this signal repeating. Basically, let's say, so how do you count something? So it's a periodic signal, right? So wherever it starts, it's a sine wave. So once it completes its whole cycle, then another cycle. So let's say you have a divide by 2 circuits. So it will give you output at after 2 cycles are over, right? So that's a basic counters kind of things. So we basically try to count with the help of those frequency dividers. There are many other indirect ways also apart from this measuring through frequency divider kind of circuit, but I am telling frequency divider because from the electronics perspective, that is what essentially we are doing. But there are many other ways also through which they can count. Okay, so basically that is like 1 second reference you already have, and then you in within 1 second this many repetitions are there, and that's how you count it.
So basically, we are measuring the frequency of the vibration. That's what you're saying.
Yes, yes, yes. Frequency of the vibration. Yes.
Mhm.
Okay. Okay, I will share my screen again. Yeah. So, any other questions? Okay, so I will go forward.
Also,
So
sir, one more
what
question.
is the crystal resonator? Okay, so so this is a left side whatever I am showing, right? That is nothing but a crystal resonator option. Crystal resonator package, which is like shown what is inside it. So you must have seen a crystal on your any of the board, or if you open any circuit, right? You will see this kind of some square box is present. So inside that, actually the key component is this quartz crystal. Okay, and then it is it is packed with this ceramic base, metal lead, and this shoulder pad. Why we need this kind of packaging is because it has to sustain all kind of vibration or temperature change or everything it has to withstand, and still it should be able to give its clock. Now, if you don't protect it, then this quartz material, right, that will have more what you can say external disturbances. So you don't want that. So that's why you want to let's say you are traveling in a truck, right? So in that case also some systems, let's say you are moving in truck, so there also you don't want your clock to lose its accuracy, right? So that's why all this casing and all these things are required, so that under vibration also or anything, it just sustains its own frequency. Okay, so that's why this kind of casing and all mechanical things will be there to protect it. But we are electrical engineers, so we will try to focus on what is this, how does it translate to our known components like L, C, and R. These three things we know, right? Basic passive things. Okay, so finally, so as I said before, right? So crystal will vibrate at certain frequency, and that we are trying to model it here. Okay, so this circuit you may identify like this is kind of a series resonance circuit, and now one more parallel branch is added. But we will just try to see what it represents and how you can analyze this particular circuit, so that if you want to build the oscillator around it, right, you have to understand how this one works. So what is the difference between crystal and oscillator? Crystal is nothing but a resonator, right, which will a passive circuit. But passive circuit itself cannot generate this kind of pure sinusoidal clock, because if you disturb it, it will resonate and then finally it will die down, right? But if you want to sustain that clock forever, then you have to replenish the energy whatever that is being lost inside this circuit. So because passive circuits will be always lossy, so if you solve the losses of the circuit, in that case you can always keep it constant amplitude, it can keep giving. Okay, but we'll not go into much detail about oscillators because you will anyway learn in your um, second or third year courses. So, but we'll try to understand this crystal resolator itself. Okay. So now let's say what is this L? So that represents the vibrating mass of the quartz. So this is L. Now C1 is a motional capacitance they call it. R is a motional resistance that they call it, and C2 is actually a capacitance. So if you have a solder pad, because finally you have to take signal out of this crystal and then you have to connect to the oscillator, and then that signal is connected. That signal will generate the sinusoidal waveform, right? So, so that is this C2 cap is nothing but this pad. If you take signal out of that, right, it will have certain capacitance associated with it. So that is represented by this C2. So now in your basic network class, you would have learned these things to analyze this any kind of this passive network. So we will just refresh it. So any circuit, if you want to analyze, right, there are two ways. First is you find out its frequency domain response and time domain response. And by the way, both are interlinked. So from frequency domain, you can go to time domain, and time domain, you can go to frequency domain. Okay, so that is nothing but through Laplace transform or Fourier transform, you can do these things. Okay, so so if you imagine this top side of this terminal, right, that you are applying the current source with respect to this one with respect to the bottom terminal. So imagine a current source here. So basically what I want to find out is what is the impedance given by this circuit. Okay. So if you want to find out impedance given by circuit, what is the easiest way? You find out a current, measure the voltage, V divided by I, that is nothing but your impedance given by this circuit, right? So one thing is you can always write this all formulas that R plus SL plus 1 by SC1, that whatever comes that you put in parallel with C2, and then you solve that, and then you get this complex formula. But we'll try to understand it intuitively, that why does it make sense, right? Okay. So if you remember your series resonance classes that might be covered in your 12th one also. So here, basically what happens at very low frequency? What is the response of this L? L is nothing but S into L. That is nothing but omega into L. So if omega is very low, then omega L is almost very less. And this R is a lossy part, and we are saying that also has to be very low, right? Because we want to, if it is extremely low, then it will, extremely high, then basically this kind of oscillation, it can't be there. It will just kill all the oscillations. So we need a kind of a second order system. So this R is also going to be very small. But what is the impedance of this C1? C1 impedance is nothing but 1 by omega C1. And similarly, 1 by omega C2. So at very, very low frequencies, omega is extremely low. So what will happen is 1 by omega C and 1 by omega C2 is very high. So initially for low frequency, if you inject the current, what will happen? What voltage it will form? This voltage drop is very small, because that is nothing but I into omega into L. Omega is very small, so this is very small. I into R is also very small, but I into 1 by omega C1, that is very large, correct? Because omega is very small. So initially what you will feel is like this, when you, for a very low frequency of the current source, effective impedance you see is nothing but 1 divided by S C1 plus C2, as if this C1 and C2 are connected in parallel. Okay. So now if you go for a little higher frequencies, so what will happen is this omega into L will start increasing because omega is increasing, and 1 by omega C1 will start decreasing, right? So what we'll do is, now if you see the sign of it, so I into omega L, and this one is what? I into minus 1 by omega C, because 1 by SC, S if you replace by j omega, it's minus 1 by omega C. So now this will try to cancel out, drop across this, right? So L will effectively try to reduce the impedance of this C. So effective impedance is going lower. So imagine a frequency where this omega L exactly becomes 1 by omega C1. Then what will
That is
happen? This
resonance
entire
frequency.
thing will become 0. Yes. Any questions?
No, sir.
Okay. Yeah. So, yes. So at a frequency where this omega L becomes exactly same as 1 by omega C, this and this will cancel out each other because they are having opposite phase, right? This is omega L and this is minus 1 by omega C. So they will cancel out each other. And what will happen? You will get just impedance will be nothing, as if like these two doesn't exist because they cancelled out each other, and that is just a R. So if you see, initially it will be following like 1 by omega C1 plus C2 kind of graph. As omega increases, the x-axis is a frequency axis, right? So as omega increases, your capacitance will go lower, and I mean impedance will go lower and lower, and finally you will at a frequency where 1 by omega L will become same as 1 by omega C1, you will just have R. So this bottom point will be nothing but a R, right? So now at that point, that is nothing called series resonance frequency. So series resonance frequency, what should be your magnitude? It should be just R. So now let's verify from this formula. So if you see this S square LC1 is there, right? If you take 1 by SC1 outside, so what will happen? SL plus R plus 1 by SC1. So 1 by SC1 and SL, they will cancel out each other. Top side, what will remain? Just R. So that is what it is. So this term is nothing called, this term top side numerator, whenever it becomes 0, imagine R is equals to 0, then this entire, this point, this impedance will become 0. So this top side term is called 0, right? So that you would be already knowing. Now, what happens after that? So after that, if you see, now omega L became same as 1 by omega C1. So now if you increase omega further, this omega into L will start dominating, and this C1 will be 1 by omega C1. So now what will happen is, what is this one also? That is also 1 by omega C2. So now this C2 and C1 will come into series, right? So that is C1 by C1 into C2 by C1 plus C2, and that will effectively again that will cancel out with whatever L is present. Okay. So now if you see across this L, you have C1, C2 and R in parallel. So now you will observe a parallel resonance that is here. Okay. And once the parallel resonance is done, after that, after the parallel resonance, it will just act like a capacitance. Okay. So that's why again you will see the reduction graph. So any crystal oscillator, right, you will always see its response like first it will do the series resonance and then it will do the parallel resonance. But only thing what is special about crystal is this C1 is going to be way smaller than C2. Okay. That means what? Your series resonance frequency is L into C1, but your parallel resonance frequency is L into series of C1 and C2, right? So if C2 is much larger than C1, then that is also going to be same as C1 itself, right? Very near to C1. So this Fs and Fp, these two are going to be very near to each other, right? So this is just I have not shown the axis, but you can imagine like if this is like 100 megahertz, this is like 100.000000001, that kind of frequency. So there is not much difference between these two frequencies. And whenever we oscillate, right, we oscillate it because it provides the high impedance here. So whatever effective R is there, that much loss, if we keep compensating, it will become an oscillator and we will get stable clock. Otherwise, if you don't keep giving it energy, just give one pulse and leave it, then what will happen? It will start oscillating, but it will die down over a time. But the frequency of oscillation is going to be L into C1 into C2 divided by C1 plus C2. Clear up to here? Any doubts?
Yes,
So
sir.
if you
So
see in
one
the
quick doubt.
yes.
So basically, in most of the crystal oscillators, you're saying both these frequencies will be very near to each other.
Yes.
But there will be some error, right?
Yes, there we want that error. On that only it works.
Oh, that error, won't it lead to phase noise?
No, no. It is because we are not operating at this frequency. See, in any oscillator, right? First thing you have to understand is oscillator, right? It works on the criteria of Bark-Hussein criterion, right? What is that criterion? Wherever
Right.
the magnitude becomes 1 and phase becomes 360, right? So that in that condition only it will oscillate. So it has to choose between this frequency and this frequency. Now if you see, this is very low impedance at this frequency, so then you have to provide that high GM to oscillate here. So it instead it will always pick up here because this one is very high impedance. Even small amount of negative impedance will be able to compensate it, and you will be able to get your oscillations, right? So it will never choose this frequency, it will always choose this frequency. And once it chooses this frequency, and if it is an oscillator, there cannot be two frequencies present together. That we have to understand. If two frequencies are present together, that is no more an oscillator, right? Oscillators fundamental is it can start at one frequency, but it can change to another frequency, but once it reaches to final frequency, right, it has to stay there. Otherwise it is not called oscillator, because oscillator's characteristic is it has to oscillate at one single frequency. Does that answer your question?
Yes, sir. Yes, sir. And one more small
Yes.
question. So,
Yes.
how is this different from a regular IC oscillator? Even there, we'll be having losses. We'll have to
Ah,
compensate with
correct. Correct.
1 by GM.
So, yes, yes. So that is a very good question. Now, so basically, whatever you can see this electrical diagram, right? Then you would think that why would I need crystal? I can myself put R, L, C, and C2. In fact, R you don't put. You will directly connect your wires, and it will only give you such R, right? So it will automatically. Then I can build this circuit by myself. Why do I need even a crystal? That's a very good question. Now, the thing is, the quality factor of this circuit, right, that is in terms of 10 raised to 6. And any inductors you take or any capacitor you take available, whatever is in market, that will not have that good quality factors, right? So if you try to build this circuit by yourself, okay, then what will happen? You will get this kind of curve, okay, but its quality factor will not be that good. Now, if the quality factor is not good, this peak will not be very sharp. Okay, it will be something like this. I have not included quality factor and all analysis, but it will be something like broader kind of thing. Now, if you have a wider kind of quality factor, what will happen? First, it will be more susceptible to noise. I mean, I am not introducing noise, but phase noise, it will have a very bad, because for phase noise to be good, its quality factor has to be really, really high. Okay. And the higher the quality factor, it is very difficult to move it from one side to another side, right? See, imagine like this. If you have a wider quality factor, then you have a center frequency. Now some disturbance comes, it can easily go this side and this side, right? But, and this amplitude also will not drop so much, right? But now, if you have very tight quality factor, in that case, if you has to move it little this side or this side, right, it will take you a lot of efforts to take it this side or this side. And if you move it, let's say, if you try to move this frequency little here, its amplitude is going to drop down here and oscillation will stop by itself, right? So that's the thing with this, that you need a very, very high good quality factor. And why do we get for crystal very good quality factor is because of the quartz nature of, quartz atomic arrangement. So I will cover how they vibrate and all. So finally they vibrate in a way that it's a mechanical resonator, and it vibrates, and its effective R is going to be really, really small. And that is the reason you get real good quality factor. And that is why if you try to build this circuit by yourself, so the in principle, you are going to put same negative or cross couple circuit here and try to compensate it. But at the end of the day, you will not get so good performance of frequency stability that we defined in ppm I'll cover in the talk. And along with that, you will not be able to get a good phase noise also. Does that answer your question?
Yes, sir, got it. 10 power 6 Collie factor is pretty huge.
Yes, that's pretty huge. Yes.
So,
Yes.
so you told like the oscillator means it has to maintain one particular frequency, right?
Yes.
So basically, you told if it is not maintaining, like so, what causes like what will be usual cause? Like suppose circuit disturbance or some bad impedance mismatch, or you're saying, or like how it, means
No.
you told right? It
Yes. Yes. So once you put oscillator, right, paired capacitance can change. You connect something, it can change, but then
you're
this will
saying
vary
parasitic
slightly.
capacitance, right?
Yes, parasitic capacitance on
Yes.
anything.
Okay,
Let's say
sir.
once you connect the circuit, what will happen? The C2 effective will be different. You are putting some additional C2 here, right?
Yes, sir.
So total frequency will be what now? C1 plus L into C1. Now C2 plus C3 will come. So C1 into C2 plus C3 divided by C1 plus C1 plus C2 plus C3. So that's how this will be determined, this frequency. Now imagine if you want to get if you want to move this frequency, how can you move it? If you have a two choice, either you put a zero capacitance or you put a infinite capacitance, right? So if you put a zero capacitance, then it is going to be this response only, right? Exactly same. But if you put an infinite capacitance, then what will happen to this frequency? This can maximum, it will come inside, right? And this curve will become almost here. You understand? Because C2 plus
Okay.
infinite cap is like infinite cap. Now infinite cap in series with C1 is nothing but C1, right? So it will become like this, and then it will
It will be
become
high
like
steep
this.
signal.
High steep signal, right? So that's the maximum you can pull it. You understand? So that's why even if you take this circuit and try to connect it outside, right? So if you take a crystal's data sheet, they say that your load on this network, that capacitance cannot be higher than something, right? Let's say they will say that your load capacitance cannot be more than 50 pico or maybe 50 nano, right? So you cannot put, you have to ensure that this capacitance extra whatever you are putting, right, that is not lesser than, not more than that. So it will have its certain restriction. So basically what I'm trying
Okay,
to
sir.
say is you cannot move this frequency a lot. In fact, you cannot increase it in any ways, okay, until and unless you put, let's say you change the temperature itself. When that changes the C1 and C2 itself, right? That
Oh, okay, sir. I
extreme
understood. So
temperatures.
basically, yes, sir. So
Yes,
basically, we can modify, but problem is like we don't have more options here to modify the impedance, like you're saying, right?
exactly, because these two
Okay, sir.
are very
Okay,
near,
sir.
they are
Yes,
like
sir.
very near
Understood.
to each other. Okay, okay.
Okay, sir. So in with respect, so therefore that is for that reason we have to maintain a stable impedance for this.
Yes, so we have, there is a maximum load specification is given for this crystal because it guarantees, right, that it will give you this much frequency stability across
Okay, sir.
temperature, across like after 10 years also, because it's a mechanical vibrator, right? It's also going to
Yes,
age,
sir.
right? So if you, let's say, put more cap than that, then it will oscillate, but then it will not
Oh,
meet your all those specifications that it can across temperature,
okay,
it might violate your frequency stability and all that, right?
okay, sir.
Okay.
Okay, sir. Got it.
Okay.
Thank you, sir.
Any other questions? Okay. So yes, it's good to ask question that makes this session interactive. Otherwise, I feel like I'm speaking in front of a screen. So it's good. Okay. So now let's move further. Okay. So now this picture you would have seen in your any wristwatches. I don't know nowadays you use digital watches, but yeah, it's a traditional old age wristwatch is there. Okay, so you can see this is a battery cell, and this cylindrical thing, this is nothing but a crystal oscillator itself. Okay, so our wristwatches also have crystal oscillator, and if you do bit searching on Google, right, you will find out that this kind of cylindrical crystal, right, they will have this 32.768 kilohertz of frequency of crystal. Okay, so now why people chose this frequency? That such a weird frequency? Usually we like to have 1 meg or 1 kilohertz, 10 kilohertz. Why this weird frequency? That is because this wristwatches started were made in long time back. At that time, these integrated circuits and all those were not so popular. But they knew the circuits. They used to build the circuits around it separately, not like physical frequency dividers and all. They used to make it. So it seems that this crystal, if you make it frequency of 732 kilohertz, right, 32.768 kilohertz, and if you divide by 2 raised to 15, what it will give you? 1 hertz. 1 hertz is nothing but your 1 second. So what, with that 1 second, your hand the wristwatch will have its 1 second ticking, right? That becomes extremely easy. So we did not have many monolithic, integrated circuits that time. So they used to put a 2 raised to 15 divided by 2 circuit on the board, and then they used to achieve this 1 second. So that's the reason they have this frequency crystal, right? Now, how do we modify this frequency of the crystal? Like it can be 10 megahertz, it can be 1 megahertz. So what we have to do is, if you take a crystal, it's a material, and if you make it thinner and thinner, you can go to higher and higher frequency. So frequency, what frequency you want, that is determined by physical geometry of the crystal. Okay. So now resonant frequency of quartz oscillator is 32.768 to 200 megahertz. This is usually this is the range quartz can give maximum, right? 200 megahertz is what you can usually see in all the data sets and commercially available crystals, right? So that much thin they can make this crystal, and that crystal can even generate 200 megahertz of frequency. Now let's see, whatever the crystal are available, right? We'll see what usually what they do. So you may see different packages. Like all I have said is, all I have example taken is SMD crystal. There is surface mount crystal. Okay. So if you see the size, right, this 3.2 mm by 2.5 mm. So it has a frequency stability of 10 to 30 ppm. I will define what is ppm, but you imagine this. The higher end, if you have a frequency stability because you want to reduce it, right? It's basically a way, okay, let me define it first. So ppm is nothing but parts per million. So 10 megahertz crystal, and we say that it has stability of plus minus 10 ppm. So what does that mean? So first of all, frequency you have to take. So this is 10 megahertz. Then parts per million means 10 ppm. So 10 out of 10 raised to 6. So that means that it is 100 hertz. So what does that mean? This crystal, this 10 megahertz crystal can move by 100 hertz across your temperature, across your 10 years duration, whatever reliability they specify, right? So that is what is the ppm. So lower this ppm is, lower this number is, that's what is the better the crystal is. Okay. So now, if you have this big of a crystal, then you can generate 8 megahertz to 50 megahertz. That frequency range you can get in this package, and it has 10 to 30 ppm. But if you see the price available, right, that is nothing but 5 cents to 15 cents. Okay. Now, if you see inside miniature mobile, so mobile also will have crystals, right? So if you see ultra, miniature, and these different packages, right? Basically, the dimensions are shrinking. If you see from tops to bottom side, right, dimensions are shrinking. So whenever dimensions are smaller, then you can achieve higher and higher frequencies, but smaller crystals cannot generate low frequencies. So here you can see it is 80 megahertz or 96 megahertz or up to 50 megahertz. So this is not a tuning range. Okay, you have to choose one crystal. It will give only one frequency, but this is the range which is available in this package. So you can choose any one of that. But once you choose one, it will give you that particular frequency itself. Okay. So now,
Sir?
if you see, yes.
Your frequency is there, right? Just a small query. For this crystal oscillator, this will generate
Yes.
like 8 megahertz to 50 megahertz, right? So just for
Yes.
example, I'm asking. Suppose if I
Yeah.
need a particular one frequency, then based on how I can make it like how I can tune my crystal to give only a particular
That's
one
what I am saying.
frequency.
So this one crystal cannot generate this many. So if
Okay.
you choose 8 megahertz crystal, it will just give you 8 megahertz of frequency. If you choose 10 megahertz crystal, it will give you 10 megahertz only. You cannot tune it. Okay,
Mm-hmm.
so that is what this crystal is. So for every different frequency, you need a different component. You have to keep buying those different components. One component, if you buy 10, that cannot be used again and again. I mean, again and again means for all frequencies.
Okay, sir. So I usually thought like based on my register's impedance matching, I am tuning the frequency.
No, that doesn't happen with crystal. You can adjust,
Okay,
but
sir.
it's very tiny range. It's like maybe you can adjust like 10 megahertz plus 100 hertz. In that range only you can do. So practically you can't tune the crystal.
Okay,
Okay.
sir. Understood, sir.
Okay. Okay. But if you see, if you want to achieve the higher frequencies, what is happening? Your dimension is still shrinking 0.8 by 0.6 mm, but the cost is rising a lot because to slice crystal thinner and thinner, like you need those kind of tools which are costly, and ultimately smaller size leads to the higher price of the crystal. So what is the crystal advantages? So crystal advantages are they give good signal purity, and they give ultra low power consumption. Okay. So because it has very good quality factor, right? What does that mean? It has very less loss. So if it is having less loss, you have to burn less current to compensate its loss. It's as simple as that. If something is low loss, you have to give less energy to compensate that loss. So that's why it takes very low power consumption, right? What are the disadvantages? So just now the question was, let's say you want to change the frequency. Then what you have to do? You have to go and buy a different part, right? So that is not very tunable. Okay. And second thing is that they are still having a very high area. Okay. So these two are its disadvantages. Okay. Now, let's move on to one more type of a crystal, that is nothing but bulk acoustic wave. So this is also fundamentally it is works like crystal only. It's just a material is different, and the way it vibrates, that is different. Okay.
Mm.
So let's compare
Sir,
this. Yes.
so before moving on to BAW, so
Yeah.
one quick question
Yeah.
in crystal. Can you move on
Yeah.
to previous slides?
Uh, this one.
Yeah. So I mean, how do we compensate for that losses? So in a regular LC oscillator, we compensate with a cross-coupled CMOS pair.
Here also you exactly put a cross couple pairs across it.
But in that cross-coupled pair, it is not so easy to keep track of the, I mean, the impedance offered, the capacity impedance offered, and both the resistive impedance offered by it and the capacitive impedance, right? Because we'll be connecting the drain and gate to it.
Yes. So oscillator in itself, right? It's a system where it will self-regulate it. Okay.
Yeah.
So once
Yes.
okay, so once you have a, let's say you connect a cross couple pair here. So cross drain and source you connect it, I mean cross couple pair drain, and then another cross couple pair you put and make a cross couple connection, right, across these two terminal, and you leave it, right? So what will happen depending on the current in the oscillator, right? That current will switch one side and another side, and it will form a square wave. Okay, and that square wave will be supplied to this crystal network. Okay, and crystal network is very sharp filter, right? So it will filter out the square wave additional harmonic component, and it will just generate the sine wave. Okay, so sine wave, once it generates that sine wave, as it is a cross couple pair, depending on the amplitude, what will happen is it will again it's a positive gain system, right? So whatever it gets, it will again increase it. The amplitude, it will increase it, right? So but it will settle at some point, right? Whenever it last signal gain becomes 1, at that time only it will stable. Okay, so cross couple pair, initial startup gain you will keep it higher, because otherwise it will not start oscillating. So let's say So basically you are comparing, if it is R, then you are putting parallel impedance less than minus R, right? Then only it will start oscillating. But that less than minus R has to become exactly same equals to R, then only this amplitude will be stable. And that is an autonomous process inside the cross couple pair. Okay, its GM will start reducing because the device is larger, the swings it builds across it, the devices itself will go into triode region and start reducing the gain of the cross couple pairs. So then you have to see in a large signal sense, like over the large signal, what I mean by over the entire cycle, effectively how much negative R it is providing. Okay, so those are bit complex analysis, but that you will learn in your master's course. But essentially, that's how it happens. So
So
once in
this
yes,
so the
understood, right?
stabilization happens the same way it happens in a regular AC oscillator. So the
Yes, yes,
amplitude
stabilization.
controlled GM.
Yes, yes. So what
Yes,
will
sir.
happen is that's a temperature changes, right? This is not going to change. But if your circuit, your cross couple pair shows different GM for different temperature, this amplitude is going to be different for that temperature. Okay, so what the
Yes, sir.
circuit designers do is they will put some kind of smart mechanism so that if the current decreases, the temperature increases, they will sense the temperature and try to pump more current or do some smart circuit innovation so that they will have a constant amplitude across temperature, across years, number of years, and all, right? So still it will have some errors, but those errors will be very small and it will be specified in your data sheet, right? Or
Yes.
whatever crystal oscillator you build it. So essentially it is exactly same as LC oscillator. You don't do very something specific about it. And what you don't get this crystal resonator alone as a component mostly. You get crystal oscillator inbuilt in it, or otherwise what will sometimes you get crystal resonator also, but then oscillator parts itself is inside the microcontroller. And so okay, so if you see a
Yes, sir.
microcontroller and it requires some clock, you put a crystal resonator, but that microcontroller will have that smart amplitude controlling mechanism or something which will keep across temperature and all, it will stabilize the GA. Okay.
Yes, sir. Got it. So basically, before shipping, we'll verify across PVT corners.
Yes, yes, exactly. They verify and then
Okay.
they ship that. So microcontroller guy will take care of its own PVT, crystal guy will take care of its own PVT. So whenever you plug in them together, they behave good.
So got it, sir. Thank you. I
Okay.
think someone else have raised the hand. Suam Rai. You can unmute and ask.
Yeah.
Sir, will we get the recording of this later?
Oh,
Yeah.
I did not
Yes,
hit
yes. I'll share the
record
recording.
message. Oh, you have
Sir, I'm
recording.
recording it.
Okay.
Yes, sir.
Okay. Okay. Fine.
Kindly register, Suam. We'll share with all the participants who have registered. Registration link is in the chat.
O- Okay, sir, thanks.
Okay.
Sir,
Yeah.
basically, whatever the crystal oscillator there, basically all in general or industrial level or IC level also, you're using temperature control or voltage control.
Okay. So that's a
Depends on
good question.
application.
Yes. Yes. Yes.
Depends on
So
application
basically,
or what?
no, no, no. So basically, there are type of crystal resonators are available. They are called TCXOs, VCXOs, OCXOs, right?
Oh
Now,
yeah, also.
TCXOs stands for the temperature control, right? So they will have, let's say, 25 ppm to 50 ppm kind of accuracy, okay? And with that kind of accuracy, it will across temperature, it can maintain that one, right? uh, because basically what TCXO is doing is it is not asking us to maintain a constant temperature. Instead, it will have a temperature sensor inside and it will compensate for its frequency drift because across crystal, right? Because crystal is also a material, right? So across temperature, this L and C are going to change. So based on this temperature code, they will have some mechanism to modify this C2, and they will try to, but as it is like based on temperature sensor, right? Temperature sensor also will have certain error, right? And in correction also there will be certain errors. So that's why they can't exactly compensate it, and that's how you get the 25 to 50 ppm kind of a number for TCXOs, right? Now if you go for OCXOs, which is oven controlled, so in that what happens is the crystal oscillator comes along with its own oven. Okay, so that oven maintains the temperature. Okay, so in that case, that accuracy is going to be really, really good. Maybe less than 10 ppm, or maybe even less than 1 ppm. Okay, so OCXOs are oven controlled, and there they take care by maintaining the temperature constant, because correction mechanism will always have its own limitations. Does that answer
Okay,
your
sir.
question?
Yeah, yeah, sir. And even these
Oh,
things are like these things are internally connected to PLL. Is that correct? That phase lock
yes,
loop.
yes, they are internally
So
connected to PLL. Yes,
basic, because this is just an oscillator, right? And PLL also, if the registers are locked, it will generate on oscillations. Is that correct?
yes, but this one is what determines the PLL output frequency. So
Yeah,
PLL
yeah, yes,
basically
sir. Yes.
follows the crystal oscillator. Yes.
Okay, sir. Okay.
Okay. Any other questions? So Subhas, do we have more time, or so
Uh,
4 is a hard deadline?
no, sir, we have more time. We can
Okay,
push it a little
so
further.
wanted to is like, I don't think I can cover the whole thing, but let me at least complete this box kind of portion, so we'll have some basic idea. Okay,
Sure,
is
sir.
that fine? Yeah. Okay.
Yes, sir. Yes, sir. I mean, as long as it's okay with the participants.
Yes. Any other have any concerns, or you want to stop or something? Please let me know. Okay. Anyways, I'm going ahead. Yeah. So basically, I am here in this slide. I want to show you that how exactly the vibrations and it happens, and how do we, what is difference about this bulk acoustic wave. Okay. So basically, both have two electrodes. Crystal oscillate. So first, why even go for this bulk acoustic wave? Because it can generate the higher frequencies. As I said earlier, right? You can only generate up to 100 megahertz to 200 megahertz of from the crystal. If you want higher frequency, either you have to put a PLL, or you, I mean, basically you need to, then PLL has lot of its own power consumption and all that, right? Because these are like very low power devices. You just want simple clock. Why do you want to have a PLL, right? So that's the reason. So if you have a high frequency crystal oscillator, that's the best. That's where this BAW technology comes into picture. Okay. So it can generate up to 6 gigahertz of kind of output frequency. So what is the fundamental difference? Fundamental difference is the material, how the material is different. So basically this is based on quartz crystal oscillator, and this is some thin film resonator. Okay, I am not expert in material science, so I won't go into details of that. Only thing I can say is the vibration of the material, right? Because that's what is finally causing the frequency. So basically, if you disturb this electrode, it will try to vibrate. So once you give a pulse to electrode, it will vibrate. So in crystal oscillator, they are going to display left and right, right? So that's how they will form a standing wave pattern. So like it will vibrate, and it's like two nodes are tied together, so they will form something kind of this kind of vibration to the boundaries of it. Okay. Now bulk acoustic wave, because of the different material, right? It's like a sound wave. Okay, so then they go like vertically. Basically, they vibrate vertically. So that's the fundamental material difference, how they react to the electrical disturbances, right? So why I say electrical disturbances, because frequency is anyway determined by this crystal itself. What is thickness of this crystal, that only determines the frequency, right? So cross couple pair is what it is doing, is it is just allowing this frequency to sustain forever. Its loss it is compensating, but frequency is determined by the crystal or this ball. Okay. Okay. So only thing we have to understand is the here in crystal it is vibrating horizontally, here it vibrates vertically, and this can give up to megahertz range, and this can give up to gigahertz range. So this, it is worth to look into the BAW technology. Okay. So now this BAW technology is not new. This foundation is in 1880, where this first piezoelectric effect. So here this material also showed piezoelectric effect. So basically, it is vibration of metal based on the disturbance that is called piezoelectric effect, right? Because it vibrates at that frequency. So in 1960s to 1980s, people developed this Bohr oscillator that can vibrate at 1 to 6 gigahertz. Okay, and it came into commercialization by, but not as a clock source. Okay, this somehow it was not used as a clock source, because it was like very discrete. So first high volume, because it's a frequency is high, right? Now if you put high frequency signal outside and compensate the loss from the outside, right? It's like, let's say microcontroller has a kind of a technology to for cross couple oscillator, right? Cross couple pair, but the Bohr element, if it is sitting on the PCB and the microcontroller is sitting on the PCB, so the 2.5 gigahertz communication, right, it becomes really lossy, and that's why it was not making sense to put this 2.5 gigahertz Bohr crystal on the PCB. That's why they were not very useful as oscillators earlier. Okay, so in 2000, around 2000 time frames, but they were used as a filters. Okay, so RF filters they were used, and for mobile technologies, right? Mobile, because of you must be knowing that the bands are very costly, and we have very limited bands like 2G, 3G, 4G, 5G, and each band means it will have certain frequency range. So telecom companies are paying like millions of dollars in auction to government to get that particular frequency range. For example, for 2G or 3G, right? Airtel had some 1.8 gigahertz band, and someone else has 2.1 gigahertz band, right? So, but the bandwidth was very small. So even because it's a tiny bandwidth, what happens is you cannot afford any noise. So if you are transmitting at, let's say, 1801 frequency, and somebody, the user next to you is using 1802 frequencies, your your output has to be very sharp. It cannot go and like it cannot have kind of phase noise or skirt remaining of this clock, right? So output signal should be contained basically. So for that, these filters were used, and that was the use by companies like Corvo and Broadcom for phone market. So they were famous for the phone market, this Bohr application. Except in 2019, Texas Instrument, what they managed is they managed to integrate this entire crystal on silicon. Okay, so you might feel that on the wafer to put this, what is there? You can put on wafer, you can put this crystal and then you can bond it, but it's not so easy. It's packaging challenge, because once you put package around it, then it's going to vibrate. And we know how crystal material, we have seen previously that how fine casing they make, right? So that it doesn't respond to the vibrations and all that. So packaging wise, there are a lot of challenges, but Texas Instrument finally figured out a way to package them inside the IC itself, right? So now, along with the resonator, they can have wafer level oscillator also inside, and that's how they started generating clocks based on this Bohr oscillator. So that was a significant milestone, and that enabled many applications. Okay, so how does it work? So this is like a piezoelectric layer in between and top and bottom electrode, and if you give a signal to it, it's going to resonate. So basically, this diagram looks really simple, that lead frame, and on that silicon die, and then Bohr, and then you with a bond wire, you basically tie it to lead frame. This lead frame is nothing but any IC you take, right? That outside whatever leads are there, that is called lead frame. It's a package basically. So it looks very simple, but to get it, it's really complicated. So finally, Texas Instrument could do it, and then they made many applications. So think like that. That's okay. So let's say, why integrated IC enabled a lot of technology, right? Mobile phones and all were not so popular before when till we could do wafer level integration, right? Because circuits are same. But if you are taking every MOSFET discrete and try to build a circuit, that is going to be a very big solution, right? So let's say you have few amplifiers and some filters. Now, if you try to build it on a board, it's going to take a lot of area. And that's the reason we mobile headset or everything will become very bulky. So if you want to reduce the area, right? So in that case, you have to integrate. You have to integrate inside the wafer, right? Inside the die. So once they figured out this technology, now you don't need a simple crystal oscillator. Inside the chip itself, you have a crystal, I mean, ball sitting inside, and that only will generate a clock source for you. And now, if you can integrate that with the other circuitry inside the same wafer, you can do many, many, many applications. Okay. Okay, so first primary applications is data centers, wired and wireless networks. So now data centers, everybody would have heard of. It's because the age of the AI, right? So this data centers. So why this enabled these applications is, you can see, if you can see in the photos, how tightly and densely packed all these boards are, right? Because thousands of processors are working, doing math for you, searching information from the internet and giving you the output, right? So it requires lot of data processing, but that requires lot of hardware. Now, if you need more hardware, you need more land, more water, everything, right? So instead, what you do is, if you can pack it very tightly, then it is possible. So what happens is, it's not that, okay, I am not saying that this technology has enabled everything. No, all I am saying is it is helping to pack more. Okay, so let's say earlier this one board was needing 3.2 mm by 2.5 mm kind of a area. Now that area of the crystal oscillator can be utilized for some other purpose, because now you have integrated this chip inside the IC itself, the bigger ICs like Ethernet ICs or processors or something like that, right? So that is what. So I am not saying that this everything is enabled by this. No, but they are helping them to make it better. Okay. So now you can see this. We are selling our current parts into this 112 Gbps and 224 Gbps SerDes kind of things. These are technologies you can search on Google. I don't have time to explain this, but they are used in this kind of applications. Okay. And the second application is PCIe and Ethernet clocking also. These are used. And they are also used in 5G, 6G design currently, and older generations also. And a lot of this clocking parts are used in all these applications as well. Now, crystal-less microcontrollers. So earlier microcontrollers, if you have to have a crystal, right? But now that is not required. So we have certain parts which can have microcontrollers, and once you have microcontrollers with a crystal, right, you reduce certain area, right? So once the area is wherever the area is asset, right, for that medical applications, right, that is like some instruments and all. You want to um, you want to make the instrument as small as possible, because it has to accommodate inside the room, inside the operation theater. So every you save, that matters, right? So they are used in Internet of Things, because the sensors and all, we are going to deploy, we are going to go into Internet of Things. So there all microcontrollers and all are going to be more and more. Now, if you need every crystal for that, that's going to take a lot of area on the PCB. So that also applications it enables. And yeah, this building automations or those kind of applications. Any questions till the here?
Sir, one small query regarding that clock, sir. This one, I mean.
Yes.
Suppose my crystal will generate on oscillation frequency. Even
Yes.
suppose in an IC, like integrated, you told, right? An IC can generate
Yes.
like like suppose it has 2 or 3 clock generators. Just example.
Huh.
So the leakage won't happen over
Leakage
like
of?
mixing up like oscillations, like that frequency will come and match with this frequency, or like some mixing.
Yes. Yes. Very good question. So
So how can I reject that? Like, what is the concept for that?
Okay, so what they do is they use different supply domains. So it remains a challenge. You are correct. So sometimes what happens is our lot of our chip based on this BAW, right? They support, like, they have 12 channels. So one BAW can generate 12 different frequencies, let's say, right? Now those frequencies are different values, so they can interfere and cause spur in each channel, right? So for that always remains a challenge. So what we have is usually it is taken care by the power supply and ground routing, and through the substrate. Okay, so mostly the leakage happens through the substrate of this silicon die, and then power sub, because you are sharing power supply and ground for different modules. That's how it gets coupled. So basically any clock coupling, right, there are two mechanisms. One is electrical coupling and one is magnetic coupling. Now magnetic coupling is not a problem because one BAW is inside there, and that is only generating all the frequencies, right? So let's say this BAW is, by the way, let's say 2 gigahertz BAW, right? And I am putting one side divide by 2 and one side divide by 4, right? So one frequency is 1 gigahertz, second frequency is 500 megahertz, right? So now 500 megahertz and 1 gigahertz, right? They will also have their own harmonics, higher harmonics. Okay, so higher harmonics usually they are not problem because usually circuit will have a trend, it will have a bandwidth limitation, and it will give inherent filtering. So it's even a square wave. If you take, right, let's say you generate 1 gigahertz of square wave, so you don't want to even reject those higher frequencies, otherwise the square wave will not remain square wave. If you filter out, it will just become a sine wave, right? So what I'm trying to say is higher harmonics are not a problem. So this BAW itself can magnetically couple to different channel, and it come as a so 1 gigahertz signal will have signature of 2 gigahertz itself, right? And 500 meg also will have, but they are its own harmonics, right? Mostly the problem is when you have, let's say, fractional one. So let's say this one BAW is generating 2 gigahertz, one guy is generating 1 gigahertz, and second guy is generating, let's say, 700 megahertz, right? So 700 megahertz harmonic is going to be 1.4 gigahertz. So that is not the harmonic of 1 gigahertz, right? 1.4 and 1 gigahertz, if it couples, it's a problem, right? So to isolate those things, what we do is we have a separate supply plane, separate ground planes, so that that entire interface of 700 megahertz, it has its own supply and ground. That's how we reduce the electrical coupling between them.
So basically maintaining power integrity for with respect to this.
Yes. And it is much easier to if ideally if you have a different PCBs, different different ICs, you can easily do it, but then you can need more area. So yes, that is always a challenge, and then there will be a spec on it that you can tolerate, let's say, minus 50 dBc of signal of other channel to first channel. So everything will have a standard that this on this channel other spots should be lesser than this level, right? So that we ensure by all these techniques. Okay. So that remains challenge. So I cannot say that okay, that spur is not going to come on the other channel. It will come, but it will be within the spec. That, let's say, we are specifying that it will be less than 50 dBc, it will be less than 50 dBc. So for the applications where 50 dBc is not tolerable, you cannot use that part. You have to use a two different dies.
Filters we have to use those.
Yes. Okay. Any other questions? Okay, I will move on. Okay, so let's talk about a few BAWs. So now crystal oscillators, I told you, right? TX, TCXO, OCXO. Basically, what I'm trying to say is it is going to vary across temperature, and there has to be some way to compensate it. Okay, so how that BAW is no different. It is also going to vary across temperature. So you need a way to fix it. So this is our device LMK5C. This is like very basic device that I am right now presenting. You can see the BAW base, there are many parts, many complicated parts, but for the sake of this talk, keeping simple, I am just talking about a very basic part. Okay, so then let's say we talk about a very basic clock generator here. So LMK6C, that's a part number here. So what is this? Is a block diagram taken from the data sheet. So there is a BAW resonator is integrated inside it. So what it does is, so basically, okay, so whatever BAW frequency we are using, right, that is 2.4 gigahertz. That is what we are using currently. Okay, so this BAW will have 2.4 gigahertz, but it will vary across temperature. Okay, it is going to vary across temperature. Okay, so now what will happen if temperature changes? BAW frequency will change. So instead of 2.4, it will be 2.39999 or something, right? But we are talking about ppm. We are talking about 100 hertz kind of accuracy, right? For 10 gigahertz signal, if 10 ppm is the spec, frequency cannot vary more than 100 hertz, right? So that like many 9999 are there, right? So we have to still maintain that kind of accuracy. So what will happen? If temperature is going to change, BAW frequency will change. Then whatever those guys are doing in OCXO or TCXO, we try to do the same thing inside the chip, because now temperature sensor also is available inside the chip, right? So if temperature is changing, board temperature is changing, IC temperature will also change. That's why the BAW is changing. So we have a temperature sensor reading. We have, and based on that reading, we have a frequency control logic, right? So now in this week, what we are doing is we are taking that and changing the, we have a fractional divider. I will talk about what is fractional divider in next few slides. But you imagine, let's say it is 2.4 gigahertz and you need, let's say 1 gigahertz, right? So what is your division factor? 2.4 gigahertz divided by 1 gigahertz, that is 2.4. So basically what this block is doing is it is dividing the frequency by 2.4. Now it won't make sense to you as of now, but there is a way you can divide it by, let's say 2.4. Let's say that divider exists, right? So let's say this frequency changes from 2.4 to 2.39, right? Because of the temperature. So what we will do? We will change this fractional divider in a way that output still remains the 1 gigahertz. So instead of fraction of 2.4, we will make the fraction 2.39, right? That is a one way to generate the, control the BAW frequency, and that's how we meet the spec of plus minus whatever is specified in the data sheet. That much ppm, it will vary across the temperature. Okay, it won't vary more than that. That's the key. Okay, so there is one another part. So that is CDC 60. This is even simpler device, right? So by the way, what is this? Why this fractional divider is? If you have a 2.4 gigahertz of a BAW, you can generate any frequency here once you program this divider. Okay, so any frequency. So crystal has what limitation? If you have a crystal, one crystal, if you buy, it has to be same frequency crystal, right? It cannot generate any other frequency. Here you change the divider, it will generate the other frequency. But right now, what yes, they are clock sources, right? What there are some parts where you can request for programmable also, but usually we have also parts available, because some customers say that I don't want to program, I just want a clock. So for them, what we do is they specify that, let's say I want output frequency of 1 gigahertz, we program 2.4 in fractional divider and sell them. So it will always give 2.4 gigahertz. So those options are there. Anyways, yeah. So basically this part can generate essentially any frequency possible. The whatever fractional it supports, it can generate in terms of 1 megahertz to 200 megahertz, in between any frequency it can generate. Okay. Okay. Now the CDC 6C. So this is a bit different. This is because fractional output divider implementation, and there are a lot of challenges associated with it. Okay, so that part is going to be costly. It is, and it will have more current consumption also. This is more like just a crystal. Okay, just like a crystal oscillator, it will have integer frequency divider. So if the BAW is going to be 2.4 gigahertz, output will be multiple of this 250 kilohertz, multiple of 250 kilohertz. So you have those dividers. So it's like multiply by 1, 2, 3, 4. If you do, you can go up to 200 megahertz. Okay. So in this case, if the BAW frequency changes, what do? You go and change the frequency of the BAW, right? So it was, I mean, it will also, you will not be able to correct so much, but as I said, right, crystal also has slight range of correction based on what TCXO does. Similarly, across temperature it manages. Similarly, for ball also, you can control slightly the oscillation, because oscillation frequency itself is varying very small. Like ball, let's say, is varying by some, let's say 100 ppm to maybe 10,000 ppm, right? Depending on what kind of ball you are using. So if those kind of things you are using, then it will have its own accuracy, but this part will determine we can get it within, let's say, plus minus 25 ppm. So it will be, it will change this wav frequency itself and get the output frequency constant. Okay. So if you compare these two parts, so this part is for high speed performance and it has very pure crystal. Basically, it has very less phase noise and it has more power consumption also. And its F out is determined by F ratio divided by integer divided by numerical and denominator. So fractional, instead of fractional, we specify it in this way. One is integer plus a fraction part. Okay. But the F out for this part is always going to be 2400 divided by n, when n is nothing but a integer. So you can get all integer frequencies for, divided, I mean, given by this formula. Okay, but this is very small, like 4 milliampere part. This takes 15 to 20 milliampere, and this one is power. If you want to shut off this one, right, it takes, in power down, it takes hardly 1.5 microamps of current, while this one will take few milliamps. Okay, and this package is also small. So this is like very simple part, can be replaced. Instead of crystal, you can use this part also for your clocking applications. Okay, any questions till here? Okay, I'll go forward. Okay, so I talked about the frequency dividers there. So let's just talk about what is an integer divider. So basically, this is a clock source. Am I audible, right?
Yes, sir, you are audible.
Yes. Okay. So yeah, this is a clock source. Now there is a, let's say we want to divide by 2. So what it does, it takes one edge, then negative edge it ignores. Again on positive edge, it will be falling down like this. So this is a divide by 2 circuit. Okay, so this is a divide by 2 clocking generator. So CDC 6C basically works on this principle. It will be like divide by 2, divide by 3, divide by 4. Those things it can do, right? Where n is nothing but a integer. Now let's talk about what is a fractional divider. So fractional divider is, okay, let's say you want to divide by 2.5. How do you divide by 2.5? So there is no circuit that can divide by 2.5. So instead what we do is, let's say you divide by 2, one cycle, another cycle you divide by 3. Okay, and you keep doing that. So on an average, what you will feel, you are dividing by 2.5. But if I give you this signal as an output, then you will not like it, because you wanted 50% duty cycle signal, right? So what it does is, this particular LMK6C part is, there is some circuits available. What it will do is, it will convert this signal into 50% duty cycle signal, and it will source this one as the output. Okay, so effectively now if you see, so this one is effectively dividing by 2.5. So output frequency is nothing but 2.5 times the input frequency. But basic division remains integer only. Only thing is that if you continuously keep dividing by 2 and 3, 2 and 3, right? So what will happen? You will see one more sporad divide by 6. Right, because this is also one frequency, divide by 5, not 6. So 2 cycles, and so this signal is itself repeating again and again. So there will be some randomization, some sigma delta modulators and all that, and they try to resolve that. You don't get any extra spur because of that. And that's why I said that implementing fractional divider is a very complex circuit. Okay, so that is the reason it's a complex circuit. So you can't, I mean, it takes more amount of power. Just 1 second. Yeah, I will reshare my screen. You can still see this one, my slides.
Yes, sir, it is visible.
Okay. Okay, so this is how we do the clock division. So this is n is equals to 2.5. So you get 50% of duty cycle. Okay, so this is how this can divide only, this part can only do the integer division, the other part can do the clock division. Okay. Okay, so let me do a quick time check. That is, okay, still we have some 10-15 minutes. Hope that is okay, right?
Yes, sir, it's fine.
Yes, sir.
Sorry?
Yes, sir,
Yes,
it
sir,
is
it is
fine.
fine.
Okay. Okay. So now let's do bit of uh, visit of Fourier series, because now from this you can tell that, let's say BAW frequency is at 2.4 gigahertz, right? So you can generate any frequency between 1 gigahertz to 200 megahertz. But what if you want to have a higher frequency more than 2.4 gigahertz? How do you do it? So let's cover that part a bit, and then I will pause. If you have any questions still here, please let me. Okay, going forward. Okay. So, what is the Fourier series? It's nothing but any periodic signal you take, and then you split it out in number of harmonics, right? There is a formula for that. Uh, Basically, any periodic signal you can represent in terms of DC cos terms, sine terms, basically in terms of their harmonics, right? So if you take if you take ideal this square wave, this dotted line, if you can see that, you can represent like 4a by pi 1 by n sine n omega naught t. What does this mean? So let's say the fundamental component n is equals to 1. That means this blue signal fundamental frequency. Then it gets added with 1/3 of 3 omega naught. So amplitude is 1/3. This is a 3 omega naught signal. So if you can see, all signals are rising together, right? That is how this edge is becoming sharper. So if you see the blue, this dot dashed line here, let me do the pointer. Yeah. So if you have the dashed line here, right? So in that case, what will happen is your that is nothing but summation of this blue curve and the yellow curve. So you can see two is forming like this. Now if you add a fifth harmonic, which is even smaller, 1/5 is the magnitude. So then you see the this pink color over here. So now if you keep adding the other harmonics, you can get the basically the square wave. So what I am trying to say is, if you have a sine wave, if you just have a sine wave, and if you manage to make a square wave, right? So you can get a higher frequencies, right? Because this square wave has essentially first harmonic, third harmonic, fifth harmonic, and everything. So if you filter out, if you let's say want to do the third harmonic, and if you filter out all other harmonics, including the fundamental, you will get the 3 times of the input square wave frequency, right? So let's say you have a 2.4 gigahertz BAW, and then you want to generate, let's say, 7.2 gigahertz of another signal. What you do is you take this blue signal, and then you make it a square wave, and then filter out all other harmonics, right? So essentially, and how we do that? So it is very simple. So if you have a sine wave, if you have a low gain amplifier, then you will just amplify it, right? But if you have a limiter, high gain amplifier, so what it will do, when the amplitude is low, it will amplify. But if it is hitting the supply level, it will make it kind of a square wave. Now, in this square wave, if you now put a filter, so if you take this square wave and take its response, right, it's going to be fundamental 3f0, 5f0, 7f0, and all that, right? Now, if you put a band pass filter around this 3f0, you can essentially generate 7.2 gigahertz of clock from 2.4 gigahertz of BAW. So now somebody says that I want to generate the second harmonic, not the third harmonic, like 4.8 gigahertz clock, right? So in that, how do we do? So any signal processing, right? Basically, if you pass it, your input signal through the non-linear system. So non-linear system, you can essentially represent like a v in into a2 v in square and a2 v in cube and all that, right? Let's put a omega t inside this one, and let's consider just two terms here, right? So if you simplify the math, what it turns out to be, finally it is going to be some DC offset, some fundamental signal, and some second harmonic. Now if you can filter out this one, then you have essentially got your second harmonic. Basically, passing your signal sine wave through the non-linear system can give you different harmonics, and from that you can get your different clocks. So that is what I have shown here. So you take an input signal, you pass it through the nonlinear half wave rectifier, and then you pass it through the filter, and you generate a 2f0 signal from the f0 signal. Okay. Okay. And how do we do that? We have a simple half wave rectifier circuit. This you would have studied in the initial first year of your college. So in that, if you see, it is whenever this diode is on, it's here. When the diode is off, it's basically off. The diode is off. Let's say it's ideal diode. So you get a 0. Then again the signal comes. So if you take this this kind of half wave rectifier and try to represent that in a Fourier series, right? You get this kind of expression. So Vp by pi is a DC, and then you have fundamental component, and then you have two harmonic component. Now I put a filter around this two f0 component, and that's how I essentially get rid of all the higher harmonics. Okay. Okay. Now that is, now it's just let's say multiply by 2, multiply by 3, right? So now let's say you want to generate any other frequency, like, and for that you don't want to keep changing your circuit, right? So what you do, we don't know. We need some kind of frequency multiplier. So in how do we do that? But we know whatever is like our normal amplifier. Okay. So if you want to, let's say, generate 1 gigahertz signal from 100 megahertz, right? What you do, you need a frequency multiplication of 10, right? So let's just see how do we get the voltage gain of 10 in first case. Then we will see the frequency gain, right? So you take a op-amp, okay? You apply an input, and then what you do is this op-amp gain can be anything. Only thing is you design this 9 kilo ohm, 1 kilo ohm, and that's how you get a gain of 10, right? So what you design is forward path, you keep a very large gain. Attenuation, you keep a resistor divider. That is nothing but voltage division. So you want, let's say 1 volt to 10 volt, you want to generate 10 of gain, voltage gain. So instead of gain in feedback, if you put a division, right? You want gain, but instead of that, you put the attenuator in a feedback path that essentially gives you the gain, right? So same principle we can apply for the frequency generation as well. Okay, so that is nothing but called PLL. So it's a closed loop amplifier itself, similar to this, but it responds to the phase rather than the voltage. Okay, and in phase domain, we need to have a large open loop gain. Now we want frequency multiplication in reality, right? Like here we want voltage multiplication. For voltage multiplication, what do? We put a resistor divider, attenuator we put if in feedback path, right? So if you want the frequency multiplication in forward path, what you do? You put a frequency divider in feedback path. So if you put a frequency divider of 10 in a feedback path, you can essentially get multiplication of 10. Okay, and that is nothing but called a PLL. Okay, so it's nothing but same kind of basic amplifier, and this is the diagram of the PLL. I'm going a bit quickly here. So these are just a few components. It will have, instead of voltage detection, it have phase detection. Then it have its own internal VCO, and then you put a divider in feedback path. So once you put a divide by n, output frequency will be n times of your reference frequency. So basically, if you want frequency multiplication, now n can be anything. Okay, so n can be anything. Now if you put an integer divider here, it will be integer times reference. If you put a fractional divider here, you get fractional number times fref, input frequency. So what you can do is you can put Bow oscillator here, and then you can generate any frequency, right? So this is not with a bow. This is in general what our team has made this part is like it can generate any signal from 45 megahertz to 22.6 gigahertz, and it has this kind of a block diagram. Here you put the oscillator, I mean some crystal oscillator. You can put a ball also here essentially, right? And after that, this is nothing but detailed diagram. Basically, it's an N divider. Then it's a phase detector, phase frequency detector here, and then charge pump. And here we have a VCO. So this is a detailed diagram. I won't go into it. But whenever you, instead of just one N, you can have a sigma delta modulator. Basically, this is a fractional N it can generate. So when it can do many things, right, and generate any frequency, instead of PLL, we give term name is synthesizer. So this is a part number LMX2830, which can generate any frequency, right? So yeah, so won't go into much detail in terms of interest of time. I will stop here for questions. Any questions? Okay. If there are no questions, we can complete the session.
Okay, guys, you have any questions? You can ask. You can unmute. You can ask, or you can put it on the chat.
So I have a quick question. I'm not sure how clear my voice will be. Am I audible?
Yeah, your voice is audible. Yes.
Yeah.
Okay, so basically, when we are having this operation, I mean, option of frequency multiplication, like we can increase the frequency.
Yes.
So I don't know how to even frame this question, but it feels a little bit counterintuitive when we have that option to even use any crystal oscillator or something of that sort. We can make some simple circuit with low frequency and then multiply it. Right? I mean, what are the downsides we'll face?
Yes.
I know it doesn't work, but what are the downsides we'll face?
So if I understand your question correctly, is like why do you need crystal oscillator in the first place, right? You can
Yeah,
make
exactly,
any low
exactly.
frequency clock, and then you can generate any high frequency clock.
Yes,
Right?
exactly, sir.
Okay. Okay. So I have not covered a very key concept of phase noise in this
Yeah.
in this talk,
So,
right?
so that's the
crystal
issue, right?
oscillator. Yes, that's the issue. So
Yes, sir.
noise, right? Crystal oscillator wise, it so okay. So all this the synthesizer that I was talking about, right? This you can see the slide yet, right? Here.
Yes, sir. Yes, sir. It's visible.
Yeah. So if you see this VCO, right? So this VCO is, so if you want to generate, let's say this is saying it can generate 22.6 gigahertz, right? So something should give frequency of 22.6 gigahertz. It cannot just like that generate, right? So this VCO essentially is here up to 11.3, and that's how we get multiplied by 2, and that's how we get 22.6. Okay. But anyways, let's say we want to generate a 11 gigahertz of signal here so that we can directly focus on the VCO. Okay. So this VCO I have to anyway make on chip. Okay. But quality factor of this on chip oscillators are right. Whatever best you can make, it will be always constrained by the metallization of inside the wafers. Okay.
Yes, sir.
So metallizations inside the die or wafer, right? Because it's like a smaller components, its thickness and everything is going to be very limited. Right? Okay. So thinner the metal are, they are going to be more and more resistive. Okay. So on-chip quality factor of all these oscillators are best case, they are going to be within 40 or 50, even at the frequency of around few gigahertz, right? So overall quality factor of this oscillator you can generate on-chip oscillators, they are going to be 40 to 50. So once you have that bad of quality factor, right, what will happen is it will not have a very clean source. I mean, it cannot generate a very clean output clock. It will have a lot of noise, right? So if you want, and another thing is that these are, how do I generate this frequency 11 gigahertz here? I also basically put some LC circuit inside. similar to whatever crystal is there, right? I also put some LC circuit inside this one and generate. But my accuracy of this L and C, because you might know that on chip, right, process variation is going to be a lot. So if you, whatever you do across wafers, right, across wafer, there will be mismatches and all that. So you can never get constant frequency in terms of ppms from on chip oscillators. Okay, so what will happen if I try to let's say I don't put anything here, and I just apply some constant tuning voltage here. I don't use this phase lock loop. Then also it is going to generate 11 gigahertz output because it's an oscillator, right? It will generate 11 gigahertz of output. I am just locking it with PLL. But let's say I don't do that. What will happen? This oscillator will not have the frequency stability of 25 to 50 ppm, what we are talking about crystal. And why crystal is able to get it? Because they have inherent mechanical vibration based structure. Or why boy is able to get it? Because that's also a mechanical component, very stable mechanical component. Now, if you, just to give you idea, this one frequency accuracy, right, across temperature and all, it can be as bad as 5%. So if you want a frequency of 11 gigahertz, I can end up giving you frequency around what, 10.75 gigahertz or something, right? That much off I can be. Okay, so if we don't want to, we want at least the frequency exactly same, right? Then comes the noise, right? So noise part I have not explained in here, but what happens is, until the bandwidth of the PLL is there, so like amplifier will have UGB, right? So until the UGB is there, amplifier will keep amplifying the signal. After that, it will attenuate, right? So other noises of the amplifier can come outside and all that. So crystal oscillator noise can directly be replicated in the output circuit with a multiplication of n, okay, only till bandwidth of the PLL. After that, noise of the VCO will dominate and it will not follow the reference. And that noise is going to be usually very bad compared to the clean source which are available off chip, right? So now what your question was, that instead of crystal oscillator, you can make a low frequency circuit at the input itself, right? But that low frequency circuit, whatever you are going to make, let's say you are going to build with a capacitance and inductance available commercially, discrete circuit, LC, same structure, same amplifier, same oscillator you are making off chip. So if you go and see the data sheet of the the capacitor manufacturer, right, what it will say, its capacitance is going to vary 2%, let's say, right? So let's say inductance doesn't vary, then your frequency at input can vary by 1%. Okay. So let's say you want 10 gigahertz of output. Instead of that, you can end up giving 9.9 gigahertz of output. And that is a variable frequency. It's across temperature, it is going to vary because whatever circuit you are going to make, right, that otherwise you have to basically have the same frequency as the crystal. Same stability as the crystal. If you try to make it a discrete components, it's going to end up like few percentage of change. So 1% means 10 raised to 4 ppm. So 10,000 ppm. So you understand, right? Crystal is having a much cleaner stability, and that is why we cannot have our discrete circuit at the input, and then we can generate any frequency at the output. But if your application say that I'm okay with 10 gigahertz also and 9.9 gigahertz also, even if it varies, doesn't matter to me, yes, in that case, you can use your low frequency source as well. Nobody can stop you in that. It just depends on the application. Does that
Yes,
answer
sir.
your question?
Yes, sir. Got it, sir. Perfect. So basically, any new innovation we do, it basically boils down to make the phase noise better or reduce the power or something of that sort.
Yes, yes.
Yes, sir. Got it, sir.
Any other questions?
Okay, I think there is no more questions, so we can conclude this session. And on the behalf of organizing team, I would like to thanks to the everyone for joining this today's industry talk. And a special thanks to the Arpan sir for sharing the valuable insights and expertise in analog design. The session was highly informative and provide us a deeper understanding of the clock systems and the practical applications of the electronic design. And I also thanks to the all the participants to their active engagements in this talk. So again, thank you for all and have a great day.
Okay,
Thanks.
I will share my slides with Shubhas,
Yes,
and
sir. Sure,
maybe
sir.
he can. Yeah, he can. There was something in chat that they wanted slides, so yeah, you can get it from.
Yes, sir. Yes, sir. We will
Okay,
share the slides. Okay.
okay.
Thank you, everyone. Again.
Thank you. Have a good day. Bye
Thank you,
bye.
sir.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank you, sir. Bye.
Bye.
Thanks, guys. See you all.